Welcome again to the Windows Performance Deep Dive channel. In this video, we deep dive into exposing how memory, specifically RAM, is used by Windows and Windows apps. For most viewers, I really recommend going to the wiki and reviewing the Windows Memory cheat sheet, and also the page on tracing reference set, which refers to RAM usage. Do pause and take a look. When accounting for how RAM is used by Windows, there are three primary ways to measure it. First, the Windows Memory Manager has a bookkeeping system to manage the RAM associated with each process. The working set is an instantaneous snapshot of that bookkeeping. The working set of a process may rise and fall as code and data is paged in and then paged out or trimmed due to memory pressure from other parts of the system. Second, the reference set is similar in principle, but it's captured and analyzed in an entirely different way. WPA, the Windows Performance Analyzer, analyzes RAM usage activity over an interval as collected from an ETW reference set trace. It can also capture stack walks of the execution, which causes code and data to page in. Third, ETW can also capture a residence set snapshot, which lists system-wide RAM usage in an instant at the end of the trace. The Windows Memory Manager gives each process its own virtual address space, filled with virtualized RAM, which is backed by the file system. In this diagram, this part of the process's virtual address space and the virtualized RAM are empty. Virtualized RAM is demand paged, meaning no actual physical RAM is used until the code is executed, or until data is read or written. Here, the process loads a module, maps a data file, and allocates a large block of heap memory. These are simply bookkeeping events, as they do not initially use any physical RAM. But this virtualization is transparent to the running process. For all it knows, all the code and data is loaded and ready to be accessed. Then, as code is executed and data is read or written, the actual bytes of code and data are paged in from the file system into physical RAM on demand. And as program execution progresses, more code and data is accessed, assigning more pages of physical RAM to the process. If our mapped data file is writable, then the modified part will eventually need to get written back out to the file system. Recall that initially loading that module, mapping that data file, and allocating that heap memory are bookkeeping events that we can capture using ETW. But a reference set trace captures instead the events of assigning new pages of physical RAM to a process as they are demand paged in. In most configurations, a memory page is 4 kilobytes in size. When memory pressure occurs on the system, the physical RAM is needed elsewhere. The Windows Memory Manager writes the modified data to the corresponding backing file. So here, the modified data in the mapped file gets written to the backing data file, and the modified data in the Windows heap allocation gets written to its backing store, the system page file. And the working set of this process is trimmed. In this case, it's trimmed completely. The physical RAM takes up residence elsewhere, though the executing code is none the wiser. And while this virtualized paging mechanism is transparent to the executing code, it nonetheless slows execution. Now understand that this extreme trimming is also what happens at the start of a reference set memory trace. The system completely flushes the working set of every running process and also of the system itself, so that we can observe what memory the apps will proceed to access throughout the trace. As the program continues execution, further accessing code and data, it automatically pages back into RAM from the file system as needed. Not necessarily all of it. The TraceMemory script uses the familiar start, stop, view, status, and cancel commands. Other options limit how much and what type of data is collected. The file reference set table and chart represent RAM used by modules, called images, and memory map data files, called map files. The trace starts at 0 because all virtualized RAM was flushed out as the trace began. Part of it then gradually pages back in as existing processes execute idle operations. Here we see the service host system services at the top with 155 megabytes, and Excel launches at the 18-second mark, quickly taking the number 2 spot with 131 megabytes in file reference set usage. We can determine why the service host processes are so hungry by enabling the Service Display Name column. And there we see the Microsoft Account Sign-In Assistant and the Web Account Manager consuming nearly 17 megabytes and 12 megabytes paged in for just modules and mapped data files, which is surprising. And we can drill into the stack walks to see what code is active. Now let's hide some extra columns and filter to just Excel itself. Here we see 118 megabytes in 202 different modules, or module images, paged in to launch the app. And again, we can look at the access stack to see what code was active and hungry for RAM. In the RAM Allocated tab, we have the dynamically allocated reference set, which is heap allocations, paged pool, that's kernel memory, thread stacks, and the like. And we see that Service Host is again near the top. Then Cortana UI. I thought I'd turn that off. Then Windows Defender named MSMPENG. Then we see Excel as it launches. And again, we can look into the most RAM-intensive system services by enabling the Service Display Name column. And we have the Access Stack column to view the tree of stack walks of the most expensive running code. Again, we filter to Excel and remove some extra columns. To get back our graph, we right-click within the series list, choose Enable, in Entire Graph, All Page Categories. That gives us a chart of the various memory page categories: page file map section, Windows heap, virtual alloc, page pool, etc. And again, the stack walk shows us which code paged in the most RAM as it reads and writes to its memory allocations. I hope you found this a useful introduction to analyzing RAM usage activity on Windows. There's more detail in the wiki at the link given here. You can find MSO-Scripts at github.com/Microsoft/MSO-Scripts. Do try it out and let us know what you find.